Imitating Interactive Intelligence from the Interactive Agents Group.
When we start artificial intelligence research, we have to ask, what do we want AI agents to do? And how will we evaluate when we're making progress towards this goal? For us, interaction is both a test of intelligence, but also the point. For AI agents to be generally helpful, they should assist us in diverse activities and communicate with us naturally.
Ultimately, we believe that creating agents that are competent at interacting with us will require that agents learn during their interactions with people. First, however, we need agents that interact capably enough that humans can play with them and want to do so.
Capable interactive agents will have applications in many areas, including robotics. But to make research progress fast and safely, we've developed a virtual environment called the Playroom, in which humans and agents can interact in diverse ways with grounded language interactions.
During each episode of interaction, the environment was randomized to stop the agent from learning about the particulars of a single instance of the Playroom.
During each episode, or each interaction, one player sets an interaction by giving an instruction to the other player who solves it. Here's an example where one player says, "Lift the plane which is in front of the dining table," and the other player does so.
Here's an example of two humans having an interaction in the Playroom. The setter asks the solver to put a boat on the bed. The solver finds the boat and does so.
To build agents capable of interacting with humans, we began by collecting over a year's worth of human-human interactive data. Our recipe for using the data started with supervised learning, where we built policies that aim to imitate the actions, both language output and motor output, of the human beings. We also developed inverse reinforcement learning algorithms, in which reward functions underlying the interactions are inferred. Using those inferred reward functions, forward RL processes are used to optimize the policies further. A further critical ingredient of our approach was the use of auxiliary learning methods to improve representations. These involve both semi-supervised and supervised learning techniques. Our approach uses no program reward functions. This was essential because many of the interactions humans engage in cannot be easily codified.
Our agents received multimodal inputs of images and textual language. They produced movement policies which allowed them to maneuver through the environment, look around, and grab objects, and a language policy which allowed them to output words over time. Our reward models were similarly constructed, taking an image and language as input and putting out a reward at every time step.
Our agents train while interacting with each other. The setter agents provide instructions to solver agents, and the reward models provide feedback to the solvers for acting consistently with those instructions. In this video, we see two agents interacting during training. The setter agent is off screen, and the solver agent is in yellow. The setter says, "Push the red duck using yellow ball," and the solver looks at the red duck, pushes aside, and gets the yellow ball to push the red duck.
Our learned reward models show evidence of understanding the tasks we use them for. In the task depicted here, the setter asks the solver to take the white robot and place it on the bed. Over the course of the episode, carried out by the agent, the reward model delivers lots of reward, depicted in blue. However, when we edited the instruction given to the reward model so that it said, "Take the red robot and place it on the bed," this instruction was inconsistent with the actions that the agent carried out, and the reward model, therefore, delivered very little reward, the gray line.
As we've said, it's not easy to program evaluations of complicated interactions in the Playroom, but we need measures of our agent performance as we develop them across time. We developed a variety of means to evaluate agents, including evaluation in which humans interacted with many agents and were able to discriminate the better ones from the worse ones. In gray, we have human baseline performance. Although the agents were worse, we see that in many cases they were judged successful by the humans.
Our resulting agents are capable of ongoing interactions with multiple instructions coming from a human. In the interaction shown here, the human directs the agent to have a series of interactions centered around one of the objects in the room. Please see the links in the descriptions below for a video of time-lapse training and further human-agent interactions.